Hello and welcome. This is our submission to the May 2021 Simio Student Competition. Today we will be quickly discussing our analysis of the given data for the problem, the model we built, its verification, validation, and results, an evaluation of potential new suppliers for oak planks, and finishing with our recommendations for the factory. Diving right in, we were provided processing times for each station in the factory, as well as supplier quality and lead times. Regarding supplier lead times, we found a nearly discrete uniform distribution for each supplier, which did simplify our inventory resupply model. Through matching the first four moments and use of quantile charts, we found the triangular distribution matched well for each workstation on the factory floor. An example of this analysis is included on the slide for the drilling station in the shelf assembly cell. It should be mentioned we did not observe large differences between like stations within a cell, nor did we find the type of wood affected processing time. But we did observe the type of shelf, specifically the dimensions, 2x2, 2x3, 2x4, did affect the processing times. One interesting case we found when fitting our distributions was the bimodal nature of the cutting station in the shelf assembly cell. The use of scrap wood, only available for 2x2 shelves, was a significant factor in the processing time at that station, with the use of scrap wood reducing cutting time by approximately 20%. To implement this unique case, we added Boolean values to the equations governing the station, as you can see in the example formula breakdown on this slide.
Now I will give a tour of our modeled shelving factory. First, orders are received daily to the sales department and release timing is facilitated with a work schedule. Add-on processes are triggered upon order release, sending subassembly request entities to each area of the plant. Each request entity is assigned a state variable according to the entity's shelving type to facilitate proper processing times at each station. Let's take a closer look at the shelf assembly area. Shelf entities flow through each workstation server. Raw materials, tracked using state statistics, are decremented upon subassembly processing. If a process is starved of raw goods, the process server will fail and production will cease until the inventory is replenished. After processing, add-on processes facilitate raw good requests if inventory store is below the reorder point and no order has already been placed for that raw material. Server entities in the raw material order area and work schedules facilitate raw good lead times and arrivals. When the raw good entity arrives to the plant, it goes to the inspection server. Inspection processing time and order quantity reduction due to quality issues are controlled with add-on processes. After inspection, the associated state statistic is incremented and the associated workstation can resume production. All cells within the plant work in a similar manner to meet the daily order demand. Below the production floor, key performance indicators are displayed along with buffer costs and quantities information to validate correct operation of the plant. Now we want to highlight a few unique aspects of our Simio model, starting with our process for managing inventory buffers. The example on the slide is the back panel attached station in the final assembly cell. Processing a shelf at this station requires a final assembly, a back panel subassembly, and wood screws. The station is modeled as a combiner object. The final assembly and back panel are represented by entities. The combiner allows entities to enter the processing area only if the shelf type of both subassemblies match. Upon processing, the model decrements the wood screw buffer using an add-on process, shown on the slide. If it is not depleted, the process decrements the inventory buffer, then checks if the buffer has dipped below the reorder point. If it has dipped below, a refill order is sent to the appropriate server. If the buffer is depleted, the combiner fails and processing is suspended until the buffer is replenished. In preparation for the challenge problem, we created a new model with the added property which supplier. This property is a Boolean value that simulated multiple suppliers within the same model. Changing the value in experimentation allowed the evaluation of different suppliers with direct comparison of simulation results in the same experiment. Here are the two representative charts tracking inventories for both the current state and DDMRP configurations. The current state shows the static reorder point and max inventory levels. The DDMRP chart shows the dynamic red, yellow, and green zones for inventory management. In both cases, when the inventory level dips below the reorder point or red zone respectively, an order is made to the corresponding server, validating that the model is placing the order at the proper time. Per the given data, orders are placed at 5 p.m. on the day they dip below the respective threshold, coordinated by a Simio work schedule. Upon arrival to the plant, materials are moved to the inspection station and inventory levels are incremented to include the materials received. Simulating the model's baseline configuration revealed that the factory was unable to meet customer demand with its current inventory policy. This policy led to a fill rate that was essentially zero in steady state, riddled with stockouts, and with throughput and production times unable to satisfy the customer demand. To further validate the model and set a benchmark for optimal performance, the baseline was resimulated with raw material lead times set to zero. After eliminating these lead times, the factory was, in fact, able to meet demand, suggesting the need for an improved inventory policy.
To use the DDMRP inventory model, we had to set two factors for each material, 14 in total. With such a large set of possible configurations, it was not possible to test each configuration manually. Instead, we took advantage of the OptQuest add-in to generate reasonable sets of parameter configurations, prioritizing fill rate in our objective function, but also accounting for inventory costs. We then evaluated these scenarios using the Kim and Nelson ranking and selection procedure, also built into Simio. We first eliminated any scenario from OptQuest that exceeded $50,000 in average inventory costs or did not meet a fill rate threshold of 65%. This left us with 8 scenarios to evaluate using Kim and Nelson, which allowed us to identify the best possible configuration. As shown in the box plots here, none of the 8 scenarios had a significant difference in fill rate. One scenario, however, did stand apart as the best in terms of inventory costs. For the challenge question, we needed to generate new parameters for the DDMRP inventory policy for the potential suppliers of oak planks. This was done in a similar manner using OptQuest to generate reasonable configurations. Using the Watson Lumber Company marginally increased fill rate. Unfortunately, this supplier increased inventory costs significantly. As a result, we found the marginal gains in fill rate with the supplier did not justify the significant cost increases. Whereas using Pacific Timber did reduce inventory costs, this was an artifact of constant stockout seen using the supplier that led to significantly reduced throughput and increased production time. We did not recommend either of these potential suppliers. Which brings us to our recommendations. We found the DDMRP system improved the fill rate, throughput, and production time. Inventory prices did increase, but the trade-off with these other metrics and the reduction in stockouts should justify the new system. As a result, we recommend the DDMRP system with the parameters we provide in our included report. Additionally, we recommend renewing their current contract with Hayes Lumber for oak planks, based on our discussion from the previous slide. One quick postscript. In our simulation, we found using the DDMRP system in our recommended configuration brings the factory to near optimal performance. The utilization of the cutting station in the shelf assembly cell in this configuration becomes the bottleneck. Further improvement is possible in the factory, but this bottleneck needs to be addressed to realize it. For example, adding a second cutting station in the shelf assembly cell. This concludes our presentation. Thanks very much for your time and consideration on this project.